Okay, so let's talk about how regenerative braking works on a DC motor. And I should say that a lot of this comes from this really awesome Phil Frost's post on Electronic Stack Exchange, and a lot of the pictures that I'm going to be using are going to be referencing this. But let me just show you. So the basic idea is you have a battery that has that can control, that is going to pump into a motor that's going to drive a motor, and there's two switches. And by throwing the switches one way, you can cause the battery to drive the motor, and by throwing the switches the other way, you can short circuit the motor. And we're going to study what happens to the current and the angular velocity of the motor. But just to give some real life example, real life. This is in my lab for my PhD program, so this is not very real life. But for this lab benchtop setup, we have a motor behind the flywheel here. This is the flywheel I kludged together, and when you drive it, let's see what happens. So it starts spinning. It's pulling about 0.8 amps, and as it spins up, the amperage decreases due to the back EMF of the motor, which we'll talk about. And then I reverse it. You can see it went up to 0.9 amps, and the motor is now spinning down. It's slowing down, and then it's going to start going in reverse. So when I reversed it, what I did was I flipped the voltage from plus 12 volts to minus 12 volts, and that's a little bit different than what we are seeing in the schematic there. But this is just the benchtop setup that I'm working with. It's essentially driven by this little what is this thing? It's a LMD 1820 IT motor driver. There's a BeagleBone Black. There's a US digital rotary encoder that uses quadrature encoded pulses, and I'm driving it with these two lead acid batteries here. Okay, so that's the the hardware setup. And let's talk about regenerative braking. So the basic idea is if you have the switches configured like this, you can run Kirchhoff's voltage law around this loop, and you can see that what you'll get is that the battery voltage, the supply voltage, equals the drop across the motor windings of the motor, plus the voltage drop across the inductor, plus the back EMF of the motor. So this back EMF of the motor is the voltage that is produced by the windings of the motor moving around in a magnetic field, in the magnetic field inside the motor, and the voltage that voltage is some motor constant times the angular velocity of the motor, this W here. On the other hand, when the motor is disconnected, when you've short-circuited the motor with the switches, you just get the Vs is just 0. So you do Kirchhoff's voltage law, and you just get this plus this plus this equals 0. If you do Newton's second law, F equals ma, on the rotation of the motor, what you get is the sum of the torques equals essentially ma, except in rotations this is the moment of inertia j times the angular acceleration omega dot. So this is the torque produced by the motor. So the torque produced by the motor on the motor shaft is however much current you're running through it times some motor constant that you would have to find. And then there's also friction that eats away at the motor, that applies a torque that is proportional to the speed of the motor. So you have essentially these two equations where this Vs that you can apply can either be the full 12 volts of the motor, of the batteries, or 0 when you're short-circuiting them. So you can rewrite these two equations in this matrix equation here, which has the form x dot equals ax plus bu, which is called a continuous time linear dynamical system, and that's something that's studied a lot by me as a control theorist, by people in the controls community. If we had sensors on this thing, and we could only measure certain combinations of the current and the voltage, of the current and the angular velocity of the motor, then we might need to model our ability to get to measure the system with this measurement equation, y equals cx plus du. So for example, if we could only measure the angular velocity and we couldn't measure the current, then then y would just be w. That would be our one measurement of the system, and C would be the matrix 0, 1, and it would be multiplying this IW, and then D would be 0. So we're not going to worry about this for now, but that's what the measurement equation is. Okay. So if we go over to MATLAB, here's our x dot equals ax plus bu. This is a state space block. This is called the state space system. And inside this, you give it the A, B, C, and D matrices, as well as the initial conditions of the current and the angular velocity, the initial conditions of the system. Now, my system, I just put in A, B, C, D here because I have defined those in a little MATLAB script, which is up here. So I using various methods, measured the motor parameters, and then the A, B, C, and D. Well, that is just exactly from here. So this is the A matrix, this is the B matrix, and so on. So that's the system. I'm assuming that I have full insight into all the states of the system. So C is the identity matrix, and D is just zeros. Okay, and the first piece of analysis that we can do is look at the eigenvalues of the system. The eigenvalues will tell us about how fast various components of the state, i.e. the current and the angular velocity, will charge up or spin up or die off. So the eigenvalues of the system are these two numbers here. This is like 1,000 and 0.01. And if we want to know how those are related to the actual physics of the system, we can look at the eigenvectors. And now this eigenvector matrix is essentially the identity matrix, and well, let me just explain what you're supposed to do with this generally if you're not so lucky to have the identity matrix. The relationship between the eigenvectors and the eigenvalues and the original matrix is that A equals V D V inverse. And if you multiply on the right by x, so your dynamics of the system are essentially AX, which is equal to VD V inverse x. So if you define a new, if you do a transformation of variables, if you essentially change your coordinate system so that this z here will define to be v inverse times x, then this is z, and you essentially can rearrange this equation a little bit to show that the system z evolves like z dot equals dz. In other words, because this is a diagonal matrix, the components of z evolve independently. They're totally decoupled. Because the two components have eigenvalues of like 1,000 and 0.01. Now, because V and therefore V inverse are both essentially the identity matrix, then Z is essentially X. What that means is the two components of the system, i.e. the current and the angular velocity, both will have corresponding rates, have corresponding time constants, like this. Now notice how similar, another testament to that is that R over L is essentially 1,000, and B over J is essentially 0.01. In other words, these physical combinations, this is how fast, this is the time constant, sorry, 1 over the time constant, for the current that you would get from looking at the actual solution of this. So the actual solution of this is going to look something like I equals e to the minus R over L times t. And the solution of this system in terms of the omega, in terms of the angular velocity, is going to be something like omega of t equals, e to the minus b over j times t. So, okay, what this comes down to is the fact that these are two very, very different numbers has implications for how the system will respond. Because R over L, so this is the eigenvalue, so 1 over the eigenvalue is the time constant, essentially how fast the current will change if you give it a step. 1 over this is about 1,000, so 1 over that is 1/1000th, and that has units of seconds, so that's 1 millisecond. So the current changes on the order of a millisecond. If you give it a step, if you give the current a step change, it'll change in about a millisecond. If you give the battery voltage, your input is the battery, whether or not the battery is connected. So if you change that suddenly, like you go from 0 volts and you connect the battery to Vs, to 12 volts, the current will change in about a millisecond. On the other hand, it takes about 1 over this is about a minute. It'll take about a minute for the angular velocity to fully finish responding to that change. So let's see that in action. Here's our system. Our system has these matrices A, B, C, D, and I'm going to apply a pulse to it. And when I run this, what I get is I'm going to do 12 volts followed by 0 volts. So I'm going to connect the battery. The system initially starts off from rest, and I'm going to connect the battery and see what happens from rest. So here you can see the angular velocity spinning up. The current shoots up immediately to about an amp, and then 400 seconds later, when this thing has almost reached 16 radians per second, which is about 2.5 revolutions per second. I'll short circuit the motor. You can see the angular velocity slowly spinning down over the course of many hundreds of seconds, whereas the current immediately slams down to almost zero. So just to show you, if we zoom in here on what happened to the current, you can see that, wow, we have to zoom in really far. I mean, the x-axis here is like in milliseconds. So here's 5 milliseconds. It takes 5 milliseconds for the current to essentially reach its steady state value of about an amp. Now, by the way, if we wanted to analytically figure this out, where we would expect the steady state value to be, we could come here, and what we want to know is, if you apply Vs from rest, where will these two numbers end up? What will be the steady state values of the current and the angular velocity? So steady state means the derivatives are 0, and you would essentially solve this equation for I and W, which will be the steady state values. So I and W would essentially be you put this on the other side and multiply by A inverse, and that's exactly what we do here. So B times Vs times A minus A inverse, and what you get is the steady state value of the current is like 0.8 amps, which is exactly what we see here. It's about 0.8 amps, and the steady state value of the angular velocity is about 16 radians per second, which is what we see up here. Okay, so and the time constants are essentially what we predicted too. So L over R is the time constant for the current, and that's L and R are both, let's see, L and R, L over R is about a millisecond, and that's indeed what we see here. In about 1 millisecond, it gets to about 63% of its steady state value. Okay, so, and you can do a similar thing for the angular velocity with B over J. Okay, great. So that is how the system responds to normal, changing of the voltages. Now let's talk about regen. So what we're going to do is, here's the idea. Actually, let's go back to my plot here. So when the motor's all spun up and you turn off and you short circuit the motor, what happens sort of in a picture here is there's some steady state current that is going around the system, and when you turn off the battery, when you short circuit the motor, that current will have to change. Now the back EMF of the motor will not change, because this is on the millisecond time scale. The angular velocity is not going to change in 3 milliseconds. And so this voltage here is going to be constant, is going to be essentially the same thing that it was before. And what's going to happen is that voltage source will reverse, over time, will reverse the direction of the current. So you'll go from some current going clockwise to some current going counterclockwise, and that'll take about 5 milliseconds or something. At steady state, there is no, you might ask, what current will eventually this equilibrate to? Well, at steady state, at equilibrium, the inductor has no say over it. The voltage drop is 0 across the inductor. And so it's essentially going to be this V over this R here. Now, in our case, the V that the back EMF voltage is going to be whatever the steady state was times KB. So that's this is the back EMF voltage that is in this picture is 9.9 volts. He's using different numbers, but for us it's KB times WSS. So it's about 0.6 volts over R. So this divided by R, so it's 0.04, and this is negative because it's going in the opposite direction. And that's exactly what we see here. If you zoom in really far, you can see that in just a few milliseconds, it goes, hang on, here we go. It goes to about minus 0.04 amps. So what has happened here is that the motor is short-circuited, and the back EMF of the motor reverses the direction of the current in a very short amount of time, in just a few milliseconds. Now it's slowly dying out because that's and it will eventually go to 0 because the resistor will burn up all of the energy. Now here's the big idea with regen. We will change before the resistor burns up all of the energy. What we'll do is we'll reconnect the battery. That current will then, for a very short time, flow into the battery. The battery, of course, is going to push really hard, and it will push hard and eventually reverse the direction of the current. But for a very short amount of time, on the order of just a few milliseconds, there will be current flowing into the battery. We will be regenerating that current. Okay, so let's see how that works. That's not shown here. This little plot just shows, we slam it down, we short circuit the motor and we never do anything again. What we're proposing is short circuit the motor, slam it down to the voltage down to 0, and then after this equilibrates down at near 0.04, we will then open the battery. We'll connect the battery again, and this negative current will flow into the battery for a very short time. Okay, so let's do that. So what I have here is the same model as before, except now we're starting out at the steady state values of the current, and so now we're spinning at like 2.5 revolutions per second, and we're putting in like about an amp, and I have some logic here that this is essentially a hysteresis band where, based on the current, we will either turn on or off the battery voltage depending on whether the current is becoming more negative or whether it's time to pump it into the battery. So I'll run this. I have a little script to run it. Blah, blah, blah. Okay, and it has finished. So let me just show you what we're dealing with here. So this, at the very beginning of the simulation, is we're at steady state, so 0.8 amps, about 16 radians per second, and then we switch off the battery. So as we saw before, the current is going to fall, and so this is just like the previous plot. Let me zoom in on sort of the critical moment here. So the battery voltage falls. It actually crosses 0 here. So this is the point where the back EMF of the motor has produced, that voltage has successfully reversed the current. Now the current is going in the opposite direction, and once it charges up enough, then we decide, okay, it is time, once it gets within, say, 5% of the steady state value here, which is in red. So once it gets within 5% of this steady state value, we will then throw the switch. We will reconnect the battery. So that happens here. The battery voltage goes to 12 volts because we reconnect it, and the battery immediately begins changing the direction of the current. So this, if we just left the battery connected from here on out, the battery voltage would go right back up to 1 amp or something. Sorry, the current would go back up to an amp. The angular velocity of the motor would spin back up to 16 or whatever. But so here it's going from negative, becoming more and more positive, and now it's 0. Now the battery has absorbed all of this current, and now the battery is going to begin spending current in order to speed the motor back up. Now that's not what we want. We're trying to regenerate energy. We're trying to suck energy out of the motor, not use the battery to speed up the motor. And so what we'll do is we'll switch off the battery again. We'll short circuit the motor, so the motor back EMF now makes now we're making this more and more negative again. The battery voltage is making the current, which was 0, more and more negative. And that's the whole idea. We're just going to go back and forth between this, between connecting the battery to suck up. Well, we're going to use the back EMF of the motor to reverse the current, make it nice and negative. And then once it's negative, we will switch in the battery, and the battery will suck up that energy. And before the current becomes positive, we'll switch it off again. So that's all there is to it. That's what regenerative braking is all about in sort of its simplest form. Now, what else to say? I guess let's see. Let me run this with slightly different initial conditions, and I can show you one more thing. If you take the current, so this is the current, and this is the voltage that we're applying. The product of that is the power that we are that the battery is exerting. Now, so we obviously want that, if we're trying to do regen, we want that to be negative. We're trying to put energy back into the battery. We want the battery to be spending negative power, meaning it's gaining it's gaining energy. So the integral of that power is energy, and we can plot those. So if I rerun this thing, let's see. I just needed to rerun this because I wanted to start at slightly different initial conditions. Here is the plot of the power and the energy. Now this is black because essentially we are never, we are only very rarely, you can see here, the supply voltage is almost always 0. We're almost always having the battery be recharging the negative amperage, the negative current, and we're hardly ever dumping that back into the battery. These spikes here are the only times when we're dumping it back into the battery. And so there's only a few, very rarely are there spikes where, we're putting in 500 milliwatts back into the battery. But if you integrate this, you can see that we are slowly pumping energy back into the battery. Now this is not very much. I mean, if you look at the slope of this is over the course of, I don't know, like 2 seconds, we are putting in something like 3 joules, 3 millijoules. So this is extremely slow. And I think I might have my motor parameters incorrect, actually. But the principle is, this is the principle. Okay, so in conclusion, the whole idea here is to connect the battery, charge up the motor, let the motor spin up to a nice fast value, and then short circuit the motor so that it reverses the direction of the current. And then when that current is nice and negative, as it's big and negative, then it's time to switch the battery back in, and the current will flow back into the battery for a very short time. And just to be totally clear, that's what's happening here. So here we are short-circuiting the motor back EMF is making the current nice and negative, and then we reconnect the battery, that current flows back into the battery, and then we disconnect the motor before the battery actually spends any energy. Okay.